What is going on, guys? Welcome back to the Python data structures tutorial series. In this video today, we're going to implement a binary search tree from scratch. So let us get right into it. Alright, so we're going to implement a binary search tree from scratch in Python today, and as always I want to start by taking a brief look at the theory, and then we're going to get into the coding. For this I'm going to use my favorite visualization tool, MyPaint, and I'm going to keep it simple here. The basic idea of a binary search tree is that we have a root node and we have left and right child nodes, and these can again have left and right child nodes. They don't have to have a child, so they can also point to none, which in terms of visualization, we would just not draw this connection. They can also have just one child node, so something like this is also possible. All of this is still a binary tree. Now, this is a binary tree in general. This is not necessarily a binary search tree now. A binary search tree also has the property that every key to the left of a node has a smaller key than the key of the node, and every key on the right of a node is larger. So basically, if I have something like 10 here as my key, it means that on the left side here, I can only have key values that are less than 10. So for example, I could have 7 here, and I could have then again here, we have the left node has to have a smaller key than this. So I can do something like maybe 2. Then on the right side, it has to be larger. So I could do something like 9. Then here it has to be larger again. So it could be something like 4. And the important thing is, of course, everything on the left has to be less than 7. So I cannot go ahead and do something like 20 here. That would not be a binary search tree. It means that everything to the left of 10, every single node here, all of this here, has to be less than 10. And on the right side, it's the opposite. So here I could have something like 20, and then here again we have the same idea. I can have something less, or I have to have something less than 20, but it still has to be larger than 10. So for example, it would be 15. That's the basic idea of a binary search tree. Now, some terminology here. These nodes that don't have any children, we call them leaf nodes. So these are nodes that don't have any additional branches going down, not a single one. And this node at the top we call the root node. So that's the starting node of our binary tree. Now, a binary tree in and of itself is not very complicated to understand. The interesting part is some of the operations. Now, searching a value in a binary tree is actually also quite straightforward. So the basic idea is, let's add a couple of values here. So this could be 4. Actually, let's make this 5. This could be 4. No, actually, let's make this 3, and then, doesn't work. Let's do 6. Then let's do 5. No, still doesn't work. Let's do 4 would work, right? Yeah, 5 and 3. There you go. So let's say this is my binary search tree. In order to find a value now, for example, let's say I'm looking for the value 6. How do I find the value 6? Well, I look at the root node, and then I say, okay, is 6 less than or greater than 10? And of course it's less than, so I go to the left. Now I have 7. Is 6 less than or greater than 7? It's less than 7. Okay, go to the left. Now is 6 greater than or less than 2? It's greater than 2. Okay, so let's go right. And here I have 6 now, so I found the value. Because of that, it's not that difficult to find values. You just have to look at the current value and then go left, right accordingly until you get there. Now, of course, if I look for a value that doesn't exist, like 8, for example, how does this work? I go left because 8 is less than 10. I go right because 8 is greater than 7. I try to go left because 8 is less than 9, but I see there is nothing here. And because of that, I conclude 8 doesn't exist in my binary search tree. Now, the keys are used for navigation. What you can do in a binary search tree node is you can also add a value. So for the data structure, we're going to see that. I'm going to have a class here, node, and this node will have a left child, it will have a right child, it will have a key, which is the value that you see here, but it can also carry any information. So I can also have a value here. And the interesting thing about this is that with a somewhat balanced binary search tree, I will be able to find things quite quickly, because we're going to talk about the runtime complexity in more detail here, but the basic idea is if I have a tree that is somewhat balanced, now this one is not very balanced, but balanced means I have a pretty, you could say symmetric tree maybe, where it looks somewhat like this. Most of the values are kind of on the same line. Most of the leaf nodes are kind of the same line. I don't need a lot of steps to get to any value. So if you consider this here, we have 3 steps maximum to get to any value. I have to go this, and this level. So to find a value. So we call this O of H, runtime complexity, where H is the height of the tree. You could say it like this, or you could say O of log n, because it's the logarithm base 2 of n. That is the height of the tree if it is balanced. Now, it's not really like this in the worst case, so that is the average case runtime complexity. In the worst case, a binary search tree could actually degenerate into a linked list, because if I have, for example, 5 as a value, and then I insert 6 as a value, and then I insert 10 as a value, and then I insert 20 as a value, and then I insert 30 as a value, you can see that I never go left because I'm always adding larger values. And because of that, I'm going right, and this is now just a linked list because it's just pointing to the next node in the list. But we're going to talk about this when we get to insertion deletion. We're going to need myPaint again. But for now, that's enough. We're going to code the data structure. We're going to code some basic functionality, and then we're going to discuss the insert, search, and deletion function again when we get to them. So let us get started by creating a Python file, binary search tree py, and let's maximize this. Let's zoom in a little bit. Let's call the first class node. The node class is something that we use in a lot of data structures. And we're going to say here now that we want to have a key, and do we want to have value? Yeah, let's also, or actually, let's not set a value. Let's just say a key. We can set the value if we want to. And we want to say now that each node can have a left child node. By default, this is going to be none. Each node can also have a right child node, which is going to be none in the beginning. The key is going to be set to the key. The value is going to be none. You don't need a value if you don't want one. But the idea, again, is you want to use something like a binary tree to be fast at finding something because you have logarithmic runtime complexity on average. And because of that, it makes sense when you find something to not just find the key, but also the value behind it. So it makes sense to have something there. And another thing that we're going to keep track of here, because it makes things a lot easier, is we're going to say self.parent. So instead of just having left and right, we also want to have a reference to the parent, so that each node here doesn't just have a pointer to the left element and to the right element. Now I'm using my mouse. But it also has a pointer to its parent node. That's going to be important, especially for deletion. It's going to make things easier. But that's the basic node class. And of course, for the representation, we're going to just implement the dunder wrapper. And here we're going to say now, we want to return an f string containing self.key and self.value. That's that. So that's the basic node class. And now we're going to implement the tree itself. We're going to say class binary search tree. It's also going to have a constructor. And this constructor is not going to take any arguments. We're just going to say self.root is going to be equal to none. So we have an empty tree. We have no root node. And that's it. Now, what we're going to do here now first is we're going to again define the signatures of the functions or of the method. So we're going to implement a contains method, which is basically going to be a search. We're going to see if something exists in the binary tree. So I'm going to say here contains self, and we need also a value, or actually a key. We're always looking for the key, even if we're interested in the value. We don't search by value, we search by key. And then we're also going to use a couple of other dunders. We're going to use the iter dunder, which is quite interesting. This is basically what allows you, if you have, let's say we have some tree. So let's say I define a tree equals binary search tree, and then I can do for I in tree. What happens when I do for I in tree is defined by this iter dunder. So that is basically what allows me to iterate. And we're going to have 3 different traversal types, so we can choose from that, but for now I'm going to just pass. Then we're going to also say representation. What's going to be the representation of the tree? It's going to be just whatever the traversal returns, but for now, again, we're passing. Then, of course, one of the most important functions is going to be the insert method. So it's going to take, oh, by the way, we need self here as well. The insert, we're going to insert a key and a value. We're also going to have a search method. So the search method is going to allow us to find the value for a given key, or to find a node. We're going to get the full node, not just the value. And then we're going to also have the delete method. This is going to work with a key as well. And then we're going to use traverse as well. Traverse is going to be a method that allows us to traverse the tree in different orders. So we're going to say order is going to also be a parameter here. And besides that, we're going to have a couple of private helper functions. I'm going to define them here as well, just so we know that they're going to be necessary. Because what we're going to do with the delete function or method is we're going to first use the search method to find a node, and then we're going to just delete it. So we're going to have a helper function, which we're going to call underscore delete. And that is going to be called by our delete method here. Then we're also going to need 2 helper methods called successor and predecessor. I'm going to talk about them when we get to them. They're going to be important for the deletion process. Or actually, I think the predecessor is not going to be relevant, but we're still going to implement it just for the sake of completeness. So successor of a given node. Then also the predecessor. Again, I'm going to define these when we talk about them, when we get to them. And then we're going to define 3 traversal methods. So these are at least the 3 that are listed on Wikipedia. This is why I implemented them here. So we have in order traversal of the tree. And then we have also pre-order traversal. And we have post-order traversal. And that is going to be what we implement in this video today. So we have the constructor, we have the contains method, which is just going to be the search method. We have an iterator, we have a representation dunder, we have an insert function or method, we have a search method, we have a deletion method. We can traverse in different ways. So this method here, the traverse method, will just call these 3 helper methods here. And the delete method will call this method, and we'll also make use of the successor. And for the predecessor, I don't think that we have a use case. Let me just double check. I think it's just implemented for the sake of completeness. So you don't have to implement it if you don't want to, but we're going to do it in this video today. So let us get started with the with the easiest one. I think the easiest thing is to just search for a value. So to just see if it's contained in the tree. And for that, we're going to implement this basic logic that I talked about, going left and right until you find something. How do we do that? Let's assume that we have values in the tree, or that we also don't have values in the tree. What we're going to do is we're going to say the current node is going to be the starting node, so self.root. And now we're going to just go left or right, depending on what key we're looking for, until we get to the place where it should be. And if we don't find it there, if we find a none reference there, we're going to just say, okay, we don't have that, so we're going to just return none. We can also raise an exception if we want to, but we're going to just return none, and otherwise we're going to return the node. So we're going to basically say if the current node that we're looking at is none, or the key of the current node is equal to the key that we're looking for, if one of these 2 is the case, we just return the current node. Why do we do that in both cases? Because if the current node is none, so if we don't have, oh, by the way, we need to do this in a while loop, because we need to do it all the time until we find this base case. So this is a little bit like recursion, but it's in a loop, so it's iterating, but it returns the moment that you find a key or end up at none. So if you end up at none, you want to return the node anyways, because it's just going to be none. So you want to return none since you don't find anything. And otherwise, you want to return the node that you found as well, because it has the key that you're looking for. So that is the base case. This is the terminating case where we actually return the current node. Otherwise, what we want to do is, if the key is less than the key of the current node, now it's not going to be none anymore because that's already the first case. So if the current node exists and the key that we're looking for is less than the key of the current node, what we're going to do is we're going to check the left node. So we're going to say if the current node left reference is none, we're just going to return none, because what we're looking for should be at the left side, at the left child node. It's not there, so therefore, or not just it's not there, but it's a none reference, which means there is nowhere to go from here, so return none, we don't find a value. Otherwise, we're going to make a step and say current node is equal to current node dot left, and then we're going to check again for this in the next iteration. And otherwise, we're going to also say, so basically this is the remaining case if the key is larger than the key of the current node, or actually is that, yeah, if the key is larger than the current node, then we're going to say if the current node dot right is none, return none, else current node is equal to current node right. So I always like to show this again visually, even though I think a lot of you guys probably already understand this. I want to make sure that everyone can follow the logic. The idea is we have a tree like this one here, and I'm looking for a value. I just go left, right, depending on if the key is larger than or less than the current key. And the moment I recognize that the key is the one I'm looking for, so when I'm, let's say, at this node and I'm looking for 2, I can just return this node. And if, for example, I'm looking for 3 now, I'm going to see, okay, 3, or actually 3 is not a good example. If I'm looking for 1 now, what I have to do is I have to go left, but there is nothing left, so I have a none value here. Because of that, I just return none, because it means I don't find the node that I'm looking for. So that's quite simple, actually. Now, the contains dunder is going to be quite simple, but it's actually going to be easier because we're not returning the node. So all I have to do here is I got to say current node is equal to self.root. And then while current node is not none, I go left and right, and then I just return true or false. So I say if the key that I'm looking for is less than the current node dot key, then I just go and say current node is equal to current node dot left. Since I don't need to return it, I can just jump immediately. And if it's none, I'm going to recognize it anyways. So then here, if the key is current node dot key, if it's larger than current node dot key, I'm going to say current node is equal to current node dot right. And if I find the key, I'm just going to return true. And if I get out of this loop without returning true, I just return false. So that's quite simple when it comes to contains. And the question now is, how do I get values into the binary search tree? How do I actually insert something? And the idea here is actually quite similar, because what we need to do is we need to go left and right until we find a position we want to insert a new node, or where we can find a node that already exists and update the value. But then we need to do some extra work. So we don't just have to navigate to the position, we actually have to create a new node there, or we have to update an existing node. So in the case of the insert method, we're going to distinguish between 2 cases. The first case is quite simple. We don't have a root node, so we don't have anything in the tree. If self.root is none, we're just going to create a new node and make it the root node. So we're going to say self.root is equal to node with key and, or actually just with key, and then we're going to say self.root.value is equal to value. And that's it. That's the insert if it's the first node to be ever inserted into this tree. Now, in the other case, I need to navigate to the position where the new node should be placed, or I have to navigate to the position where the existing node with this key could exist, and then I have to update the value. Now you can also implement this in a different way. If you try to insert something that already exists in the tree, you can also maybe say, okay, in this case, just raise an exception because I don't want to allow for duplicate keys. We're going to just say, in this case, update the value of the existing node. So we're going to say now the root exists. So what we're going to do is we're going to play the game with the iteration again. We're going to say current node is equal to self.root. And then we're going to say while true, we're going to go left and right depending on where our key is. So we're going to say if the key that we're looking for or that we're trying to create is less than the key of the current node, we're going to do the following. If the current node has a left child node, so if current node dot left is, or actually let's do it the other way around. Let's say if the current node left does not exist, that means that now I have the position where I have to insert my node, because I am at a node where the key I'm trying to create is less than the key that the current node has, which means I have to go left, and there is nothing left, which means that I have to create my new node there. So if current node dot left is none, we're going to create a new node here. So we're going to say current node dot left is going to be a new node with the key current node dot left is going to be equal, or current node left dot value is going to be equal to the value. And then this new node that we created should point back to the current node as the parent. So we want to also say current node left parent is going to be equal to current node. So that is also an important reference. And then important, we want to also break out of the loop. So we want to say break. Otherwise, if I want to go to the left, but there already is a node there, we're going to say current node dot left, or sorry, current node is equal to current node dot left. So that's the case for the key being smaller than the node's key. Otherwise, if the key is larger than the current node dot key, then we can just copy all of this here and replace left with right. So I'm just going to use here substitution. Left is going to be replaced by right. And that's now the difference here, because now same game, we want to go right. Right doesn't exist. Perfect. Create a new node, update the value, update the parent reference, break. Otherwise, go to the right. And then we have a final case, which is that the key is exactly what we're looking for or what we're trying to create. In this case, we just update the value of the current node. So current node value is equal to value, and break again. That is the insert logic. So again, what's the logic behind this visually here? I want to insert a new node. Let's say I want to insert the node 1, or actually let's go with, can I do 8? Let's do 8. How do I create a node 8 with a key 8? What I do is I go to 10. I see, okay, if I want to insert 8, I have to go to the left. Can I insert it here directly to the left? No, there already is a node here, so I cannot insert the node here because 7 already exists here. So go there, see that 7 is 7 and 8 is larger than 7, so I have to go to the right. Can I just create my key here? No, there exists a node, so it's not a none reference. It's 9. Okay, 8 is less than 9, so I would have to go to the left. Can I go to the left, or is it a none reference? No, there's nothing here. Perfect, create a new node 8. If the node already exists, so if, for example, I wanted to insert 9, I can see that this here is 9, so all I can do is I can just update the value of 9. Value update, because 9 already exists. These are the two cases that we can have. All right, so that is not too difficult. The most fancy thing here is the delete method, which I think actually we're going to talk about next. Yeah, I want to talk about delete next, because delete has now 3 cases that we need to handle differently. And by the way, regarding the runtime complexities, I'm going to talk about them in the end. But for now, I just want to implement the functionality, and then we can talk about the complexity of that and the average case and worst case. But I want to talk about, or I want to implement the delete method first. And the delete method is interesting because we have basically 3 different cases, and these are the following. So I have a very simple case, the first case, where I'm deleting a leaf node. So let's say I have a tree like this. I have 10, then maybe I have 5, and then maybe I have 15 here, or actually let's go with 20 so I have more space. Then let's say I have maybe here 2, maybe I have 7 here, and then maybe I have 9 here, and maybe I have 12 here, and then I have 30, and then I have 22, 21, 23. I'm just adding a couple of notes here to also highlight the other examples. Let me delete all of this here. And then maybe we have 35, whatever. Deleting a leaf node is super simple because I just have to remove the node and that's it. So if I want to remove 2, if I want to remove 9, if I want to remove 21, 23, 35, all I have to do is super easy, cut the connection. So cut it in both directions. Remove the reference from 5 to 2 and remove the parent reference from 2 to 5. That's it. Done. That's the most simple case. The second case is I delete a node, with one child, exactly. So that would be, for example, 7. If I want to delete 7, because 7 only has a single child, that's super simple as well, because all I have to do is I have to delete 7 and I have to redirect the connection. So I cut the connection between 7 and 5 again. I cut the connection between 7 and 9 in both directions as well. And then I add a connection between 9 and 5. So I just replace the node I'm deleting with the only child node. I don't have to make a decision here. It's super simple. I just replace 7 with 9. So in this case, I just replace this node here with 9. Super simple as well. The third case is the only one that's kind of tricky. The third case is I delete a node with 2 child nodes. And in this case now I need to do the following. I need to replace the node I'm deleting with its successor. So that's a new term that we already talked about in terms of function, in terms of the function name. But a successor, the successor node, is the first node, or you could say the smallest node that has, or the node with the smallest key that's larger than the key I'm replacing. So in this case here, I'm replacing, let's say 20. 20 has 2 child nodes. In order to replace it, I go to the node that is the smallest node that is still larger than 20. And in this case, that's 21. So 21 is the successor of 20. Why? Because it's in the right tree, the leftmost node. Now, if 21 didn't exist, I would replace it with 22. That would be now the successor. So I'm replacing it with the smallest key that is still larger than the key I'm replacing. That is how you handle that. So in this case here, it would be remove 20, replace it with 21, and remove 21 from down here. In the other case, if I didn't have 21, I would say, so if this doesn't exist here, I would say remove 20 again. And now replace it with 22. And of course, what happens then is that I have to also shift this up. So that's that. So we want to replace everything. We want to replace the node that we're deleting, if it has 2 children, with its successor. Now, for the sake of completeness, we also talked about the predecessor. And the predecessor is the opposite. It's basically the largest node that's smaller than the node. So it would be, the predecessor of 10 would be 9 because it's the largest node that is still less than 10. So this is something that we're not going to use for anything, but just for the sake of completeness, we're going to implement this as well. But for the successor, it's the smallest node that's larger than the current node. So let's put all of this now into code. In our delete method, we're going to first find the node if it exists. So we're going to say node is equal to self.search key. And if the node is not found, so if node is none, we're going to raise a key error because we're trying to delete something that does not exist. node with this key does not exist. And otherwise, we're going to call the helper method underscore delete onto the node. Actually, why is this key? It should be nodes. So we want to call this with a key, but that should actually delete a node object. So we actually want to work with a node, not with a key. So we find the node using the key, but then we want to actually delete the node itself. And what we're going to do now here is we're going to define these three cases. The first case is node is leaf node. The second case is node has one child node. And the third case is node has two child nodes. So if the node is a leaf node, how do we actually check for this? We say the node left is none and the node right is none. If that's the case, it's a leaf node because it doesn't have any children. And in this case, we're just going to check for the special case that the node that we're deleting is the root node. So if node.parent is none as well, we're just going to say self root equals none. That's the special case. Otherwise, it's not the root node. So what we're going to do is we're going to say if we need to determine which node of the parent node this is. So let me show this visually again. I need to use my drawing template quite often here. If I have a node that I'm deleting, so let's say I have 10 here and I have 5 here and I have 20 here. Let's say I'm deleting 20. If I'm at node 20, I of course have to set the reference of the parent node. So in this case of 10, the right needs to point to none after this. But when I'm at 20, I don't know if 20 is the left or the right child of 10. I only know that if I'm looking at 10, because then I can see left and right. But if I'm looking at 20, 20 just tells me my parent is 10. It doesn't tell me I'm the right child of 10. And because of that, we need to check for this. So we're going to say if node parent right is equal to node, then we're going to say the following. Node parent right is going to be none after this. Otherwise, node parent left is going to be none. And in any case, I'm going to say node parent is going to be equal to node left. No, actually, this doesn't make sense. Sorry, node parent is equal to none. Again, idea is I'm looking at the parent. I want to know, am I the parent's right child or am I the parent's left child? Depending on that, I'm going to set the respective reference of the parent to none because this node is now deleted. And of course, I also want to remove the reference from this node that I'm deleting to the parent. So I set this to none. The second case now is that I need to use an elif here because it needs to be still connected to the if statement. We're going to say if node left is none or node right is none. The reason I can do that here is because usually that would not be enough to check, but since I already have excluded the case that both are none, since I have the if statement here, if I get into this, one of them is none and exactly one of them is none. Because if both were none, it would get into the if, otherwise it gets to this checking here. So if still one of them is none, exactly one of them is none. So I can say that the child node, since there is only one, is going to be node.left if node.left is not none, else it's going to be node.right. So the node that is the child node of the node I'm trying to delete, there is exactly one, so I can determine if it's the left one or the right one, because one of them is none, the other one is not. And again, here I have the special case that the node I'm trying to delete here is the root node. So if node.parent is none, that basically means that the node is the root node, because the root node doesn't have a parent. In this case, I have to say that the child node's parent is going to be none as well. Because basically if I'm trying to delete, let's say I have 10, the root node, and let's say I have 20, the only child node of that, if I'm deleting the root, of course, that has to now point to none as the parent because that is now the new root node. So I need to say that, first of all, the reference to the parent has to be set to none, but then also self.root needs to be that child node. Otherwise, I just have to do the following. I have to say again, if the node parent left, or we did right first last time, so let's do right again, is this node that I'm trying to remove, then I need to say the node parent right is equal to the node. Otherwise, node parent left is equal to node. And now we do the following. We say child node dot parent is equal to the node parent. This is clear. But then we also need to say that the node parent is equal to the node left is equal to the node right is equal to none. So this is just killing the node. I'm removing the node. The basic idea here being that my node that I'm trying to delete has a parent. Actually, sorry. I need to set this to child node. Okay, so my node that I'm trying to delete has a parent. So this node is either the right child or the left child of this parent. And what I want to do now is I want to redirect this reference, whatever it is, left or right, to the child node. Since I only have one node, I know which one to redirect it to. So again, maybe before I talk too much here without visualization, the idea is I have 10, 20, and 30, let's say. I'm deleting 20 now. So I need to redirect the reference here. It's the right one in this case. I need to redirect it to this child node. And then I also need to set the child node's parent reference to the parent that it was before. And then I need to cut all the connections. I need to cut this one. I need to cut this one in both directions. So all of this needs to be cut. The reason we also set this one to none is because we don't want to check necessarily if it's the left or right node. I just set all of this to none. Parent, left, and right are set to none. That's definitely going to be true. And I redirect the connections here between parent and new child node. The last case I have here is that I have two child nodes. And this is now where the successor function or the successor method becomes relevant. So before we implement this branch, I'm going to say pass, and we're going to implement the successor method. It's actually not that difficult. Because think about it, I'm not sure, do I still have the drawing here? Yeah, think about this. In order to find a successor of a node, all I have to do is I have to go right once, because remember, it has to be larger than the key of the node I'm currently at, but then it has to be the smallest possible value. So to find a successor, I go right once, and then I go left, 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 until there's nothing there. So in order to find a successor, I say if node is none, I will raise a value error because cannot find successor of none. But otherwise, I'm going to say, actually, I don't need an else branch. I can just do it like this. If the node right is none, then I don't have a successor. So if there's not a single node that has a larger key than the current node, then I'm not able to find a successor. Otherwise, if there is a right node, I'm going to say current node is equal to that right node. So go right once, and then while we have current node dot left, so while that exists, say current node is equal to current node dot left, and in the end return the current node. So again, go right once and then go left all the time. This will inevitably lead to the successor. So if I look at 10 here, what's the successor of 10? Go right once and go left as long as you can. And of course, if I had, for example, 11 here and 15 here, then I would do the same thing. Go right once, left, left. If I'm looking at 22, go right once, left. And go left as much as you can. In this case, there is no room between 22 and 23 if you're using integers. But the idea is go right once to make sure it's larger than the current key, but then go left to get the smallest value possible. That is a successor. Now for the predecessor, it's actually basically the same thing in the other direction. So I can copy that, and the only thing I have to change here is I have to go left once, and then I have to go right all the time. And that's how I find the predecessor. So that's quite simple. And we said that if we want to delete a node with two child nodes, all we have to do is we have to find a successor. So I can say successor is equal to self._successor of the node I'm trying to delete. And then all I have to do is I have to say the node key is going to be equal to the successor key. The node value is going to be equal to the successor value. So I replace the key and the value of the current node with the key and the value of the successor. And of course, if you have other fields here that are relevant in terms of data, so something like, I don't know, some file pointer or something, anything that belongs to the content of the node, you want to copy it here, and afterwards you want to delete the successor. So basically what's going to happen here is, let's say I'm trying to delete 22. What I'm going to do is I'm going to delete the key and the value of 22. So whatever is in here, I'm going to wipe it clean. And the successor is 23. So what I'm going to do is I'm going to copy the value here, 23, and whatever the value is, like hello or something. And then I'm just going to delete 23. There you go. That's the basic idea. And since we have the delete method, this is going to be done properly. So if it's a leaf node, it's just going to delete it. If it has exactly one child, it's going to shift it properly, and it cannot have two children, because then I could go left one more time. And yeah, because basically if you try to delete the successor, it can either have one child, the right child, or it can have no child. So it's a leaf node. And that is our delete method. So we call it here, we find a node here with a search function, then we delete this node, and the deletion happens in these three cases. All right, so the last thing that we need to implement before we talk about the runtime complexities is the iteration, and of course also the representation, but the representation is just going to be a string version of the iteration. So let us implement the traversals. And we're going to actually do that here as generators, because what I want to do is I want to be able to iterate over it. And because of that, we're not going to return, we're not going to just print, we're going to actually yield. So we're going to yield from the traversal functions. So the in-order traversal is basically, you want to go through the left subtree first, you want to go then to the root node, and then you want to go to the right subtree. So let us see what this would look like in our example tree here. The in-order traversal is actually quite intuitive. Again, remember, we go left first, then root node, then right. And this basically means we go left, left, there you go. Then we go root node. So root node in this little subtree here is 5. Then we go right. So we go to the lowest level. Then here we only have a root node, so we print this. Then we go up, so we have left, root, right. This is left, root, right. Now, right here is again left, 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 root, right. Then root, since this is left. Then here again, left, root, right. And if you look at the numbers, that is why it's called in order, because we go 2, 5, 9, 10, 11, 12, 15, 22, 23, 30, 35. So we go in ascending order. This is just the ascending order. That's why it's called in-order traversal. Now the pre-order traversal is root node first, then left, then right. So it would be 10, 5, 2, 9, 22, 12, 11, 15, 30, 23, 35. Yeah, so that's the pre-order traversal. And the post-order traversal, is now left, right, root. So we go first 2, then 9, then 5. So 2, 9, 5. Then we also don't go to 10 yet. We go 11, 15, 12. Then we go 23, 35, 30. Then we go 22, and then we go 10. So that's the last thing. The root node is always the last thing. And these are the three methods that we're going to implement now. So we're going to go into our code again. And here we actually need to change this now to accept the node argument, because we're going to call this recursively. I'm going to explain here in a second why. The basic idea is I actually already said that while showing the visualization, but every node can be considered a subtree. So if I do the in-order traversal, we said we go left, root, right. We do that on for every node. So if we only have one node, that's the only thing that we can return. But otherwise, we can consider this to be left, this to be right, and this to be root. So first call is left, root, right. And since this is the first one here, I do the same thing. I have this subtree now, left, root, right. And in here, I do the same thing. So I do this, I do root, and then I do here again, left, root, right. And then within this tree again, left, root, right. So this is why we call this recursively. Now, there is a caveat to this, because we're not actually returning, we're not just printing, we actually want to yield the values, we want to generate these values. Now, for those of you who don't know what generators are in Python, I'm going to briefly open up an interactive shell here to show you. Let's say I have a function gen, and this function just iterates for I in range 20. Now, I don't return these values, I don't print these values, I want to yield them, I want to generate them. So instead of printing them, I can just say yield I. Now, what does this do? What this does is when I create my generator object here, I can iterate over these values. I can get the next value. So I can use the next function onto my generator to get the next value from this loop. And I can also iterate over it. So I can say for x in my gen, and then I can just print x. And this will now no longer give me 0 and 1 because I already used those, but I will get 2, 3, 4, and so on up until 19. That's the idea of a generator. I generate values, I yield values. And we can also do that recursively. So what I do here is I say if the node is not none. What I do is I call this function recursively. So I say, or this method, self.inOrder traversal on node left. So we go again, left, root, right. That's the in-order traversal. So I also do that on right, but in between I also need to yield the node that I'm currently talking about. So the node that is currently my root node here. So I say yield, and then this node's key and this node's value. That is going to be my base yield case. However, I also want to yield whatever I get from here. So in order to yield everything I get from this call and everything I get from this call, we use the syntax yield from. So this basically yields whatever these functions yield, or methods. If you're confused by that, if you don't know what I'm talking about, you can watch a video on generators, you can watch a video on yield from. I do have videos on this on my channel, but I'm not going to explain generators now here in more detail. But that's the basic idea here. We want to yield the values in this order, and then I can just copy paste this to my other methods. So I can say, in this case, I keep everything the same, but for the pre-order traversal, I yield the node first, and then actually I need to change this then to pre-order traversal as well. And you need to consider, of course, this order of left, center, right is, of course, then also recursively applied within these function calls. So it's always this principle, the same thing that I showed you in my paint. And then for the post-order traversal, all I have to do is I have to change this to post-order, and this needs to be yielded last. So these are the three traversals. And to actually do a traversal now, I need to call them. So I need to call them here in the traverse method. So we're going to say here, if order is equal to in order, then we're going to say yield from self dot in order traversal starting at the root node. Elif, the order is equal to pre-order, yield from pre-order traversal roots. Elif, the order is equal to post order. I'm gonna yield everything from the post order call. And if I get anything else, I can raise a value error unknown order. There you go. So that's how this works. And now finally, we can also implement the iter and the representation dunder. This is quite easy. All we're going to do for the iteration is we're going to say yield from, and then self.inOrder traversal is going to be our default of self.root. And then we're going to say yield, here actually not yield from, we're going to say for the representation, we're going to return the string version of the list version of whatever we get from the iterator. So, or not from the iterator, from the generator, self root. So we call the in order traversal onto root, we turn it into a list. You can turn a generator into a list. It will just generate all the values and store it in a list. And then we can turn that into a string and return this. So that is the implementation of our binary search tree. Now let us talk about the runtime complexities. We already talked about them in the beginning. The basic idea is when I have a tree, my average case runtime complexity and my worst case runtime complexity are different. Now if I start at the value 20 and I go left, right, and I append 10 and 30, and I do that in the perfect balanced way, 5, 15, and 25 and 35. If I do that like this all the time, I keep the balance by inserting the values in a specific way, then I will have a balanced tree, and the height of that tree will be the logarithm of n. So the height in this case will be the logarithm of n, base 2, and I will only have a very small number of levels compared to n. However, if I do it in an unintelligent way, so the same values inserted like this, 5, 10, 15, 20, 25, 30, 35, now the height of the tree is actually n. So I have as many levels as elements, which is not a good thing. So in this case, I actually end up with a linked list. And this is an actual case. This is a real case. It can happen. So that would be a worst case runtime complexity of n for basically anything. For searching, because if I want to find the value 35, I have to go through all n elements. For inserting, if I want to insert 36, for example, I have to go all the way to the end. For deleting, if I want to delete 35, I have to go all the way to the end. So in the worst case, I have an O of n linear runtime complexity. If I want to do this in a balanced tree, so in the average case, if I consider the average case to be the tree is somewhat balanced and I have a height which is logarithmic in terms of n, that would mean that I only have to go a logarithm of n levels low. So that's a very good runtime complexity because all I have to do now is, in this case, I have 1, 2, 3, 4, 5, 6, 7 elements, and I only have 2 levels, which means that I only have to make 2 decisions to get to any node. If I want to delete 35, I go right, right. If I want to find 15, I go left, right. I only have to go a maximum of 2 actions for 7 elements. That's the idea behind this being an average runtime complexity. So in the code, I'm not going to now add all the comments here, but basically for all these things here, except for the iteration and the traversal is always going to be linear because you have to go through all the elements. So actually, let me add some comments here. This is always going to be O of n. This is always going to be O of n, because in order to go through all the elements, you have to go through all the elements. So this is going to have a linear runtime complexity. This is going to have O on n in worst case and O of log n in the average case. And it will have O of h, so O of height, always. And I can copy this now and put this over insert. I can put this over search. I can put this over delete. Traverse is going to be linear. And these are now just the helper methods. And for the successor, of course, you could also argue in order to find a successor, you have to go a certain number of steps on average, or in the worst case, but these are now the methods. So linear runtime complexity, no matter what for the traversals. Otherwise, average case is log n, best case, not best case, worst case is linear, and it's always linear in terms of height, but the height depends on how you structure the tree. So that's the implementation. Now let us move on to the actual experimentation. So let's actually see if this produces some problems. If name is equal to main. And now what I'm going to do is I'm going to reconstruct the tree that we're constantly talking about here. So this tree up here. So we insert 10, 5, 22, 2, 9. So let's say BST is equal to binary search tree. And now BST insert. And I want to insert 10 in the beginning. And let's say the value is always going to be just hello or something. You can use different values if you want to. But we're going to say 10, 5, 22, 2, 9. So 10, 5, 22, 2, 9. And then we have 12, 30, 11, 15, 12, 30, 11, 15. And then we have 30, 23, 35. Was it 20? Not sure. No, 30, sorry. 30, 23, 35. All right, so that's the tree that we already have in our MyPaint sketch. And now we can actually see what happens if I say print, or actually for the traversal, this is also an iterator. Yeah, so let's say for I in BST traverse in order, what does this look like? Print I. We should see all the numbers in ascending order. And in this case, I get a problem because in line 11, I have some issue with the representation. That is because I have an extra curly bracket here. Now let's run this and I can see 2, 5, 9, 10, 11, 12, 15, 22, 23, 30, 35. So that works perfectly. Now let's go for the pre-order. We talked about what this should look like. So let's actually move this to the left. Let's move this to the right. And we can see now what it does is it says first the root node 10, then 5, then 2, 9. So we have the structure of first the root node, then the left, but of the left, of course, also the first root node. So we go 10, then we go left, but we don't go left all the way. We go first the root node again, 2, 9, then we go right, first the root node again, 22, 12, and then 11, 15, 30, 23, 35. And for the post-order traversal, it's going to be the same post-order. It's going to be the root node last. So 10 is the last, as you can see. And you can go through it and see that it works as well. So the interesting thing would be what happens if I now delete something. Now, if I delete, let's say, what would be an interesting thing to delete? Let's start with the base case. What happens if I delete 9, which is a leaf node? That shouldn't be too difficult. And now actually, let's go with pre-order traversal to see if this still works. If I delete 9, what happens is I get still 10, 5, 2, I don't get 9 because 9 is deleted, but the rest of the structure works. Perfect. Now let us delete not 9, but something with 1 child. We don't actually have something with 1 child. So actually let's append another node, bst insert, and let's insert 1. The reason for that is I want to have something that I can check the case with. So I would have 1 here. And in this case, let's also delete 1 again. And yeah, basically nothing changes. Or actually, sorry, I didn't want to delete 1. I wanted to delete 2. Because now 1 should replace 2. Wrong key. There you go. So now I have 10, 5, 1, 9. Because 2 is no longer there. So this works as well. And now let us go ahead and remove 22. What should happen? Remember, we go right and we should replace it with its successor. It should be replaced by 23. So we should see 10, 5, 2, 9, then 23. So let's remove 22. And we have a problem. So there is a problem with the implementation. Let's fix that. Okay, I found a mistake. We should call the underscore delete method here when we delete the successor and not the delete method itself, because this one here takes a key and this one takes a node. So we actually want to delete the successor node that we find here, which means we want to call underscore delete successor and not delete successor. This should resolve the issue. So let's put this here again. Let's run this. And now we can see what happens when we remove 22. 23 moves up. So we have 10, 5, 2, 9, and then we have 23. So of course this doesn't exist anymore. So 22 was replaced by 23, and then we go on with 12, 11, 15, and then 30, 35, because we don't have 23 here anymore. So that works perfectly fine. And we can also print the tree itself, which is just going to give us a list of the pre-order elements here, or not pre-order, in order elements, in order sorted elements here. And besides that, I think we tested everything. I mean, the search, we could try the search. Print bst search, and then give me the value of 30. In this case, it's just going to give me the node with 30 hello. So yeah, this is how you can implement a binary search tree from scratch in Python. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.